Hi class, we are now on chapter 2.1c. This is describing the quality of measurements. Measurements are essential in chemistry. Nothing would pretty much exist without measurements. And if you continue with chemistry, all you're ever going to deal with are measurements. So you have to know how the rules go in understanding when you're at what you're looking at with measurements. Some measurements will have more numbers to them, some will have less, and you have to understand what that means. In this section, we're going to look at measurements and the quality of them is pretty much what we're going to look at. So precision and accuracy. Accuracy is how reliable a series of measurements are to the true value. So how reliable a series of measurements are. So you take several measurements. So a series of measurements is what they would call them. And then you take the average of those measurements. Precision refers to how close a group of measurements are to each other. That doesn't necessarily mean they are close to the accurate, correct answer, but if they're all grouped together, they are more precise. They are more closer together and grouped. Accuracy is how close they are to the true value, the real answer. So if we look at an analytical balance, and that's what this top thing is called, an analytical balance. And what you do is, this is glass, and it prevents any wind or any kind of air being moved. That it's so sensitive that the air can change the numbers on the balance. So you open any of these, it opens on this side, there's a latch here, there's a latch here, and there's a latch here. Then you close them all, and this is a tear button, and you will be able to see numbers. And the more numbers you have, the more precise the answer is. The less numbers, think of it as more vague. You don't know. Are you 200 pounds or are you 215.23 pounds? The more numbers give you a more precision, which means it's more detailed. Less digits, less detailed, less precision. So there's a big difference between an analytical balance, which as you can see goes to the tenths, the hundredths, it goes on. And here you have only in the tens place for an animal scale. So which of these is more precise? It would be this one here, obviously, because I just said the measurements with more digits is considered more precise. So an analytical balance is more precise. This balance measures within 1/10,000th of a gram, where the animal scale measures to 1/10 of a kilogram. So it's not going to be as precise as this. So again, what is the difference between these? This is how reliable a series of measurements are towards the true value, the correct answer, if that helps you understand it. Precision is how close a group of measurements are to each other. They don't necessarily have to be near the correct answer, but they are grouped together. So you may do an experiment and you may have, and this happens all the time, you may measure and remeasure 3 times, and your answers are all very close. So you think that you're correct in your experiment, only to not get that part graded well because you're actually very far from the real answer. But your precision was good because all your values are close to each other. So if we look at a dartboard, I don't know, I forgot what this is called in your book, but I look at it as a dartboard, or the arrows, if you're shooting arrows. And here is something, this first one is accurate and precise. Why is it accurate and precise? Because obviously the bullseye is in the middle. So every shot is close to the correct answer, which is everything wants to be aimed in the bullseye. It's also precise because all the values are grouped together. They're very close to each other. Now if we look at 2, this is precise but not accurate. This means that you're away from the correct answer, which would be the yellow part, which is the bullseye. But all your values are very close together. And this, like I said, happens in experiments a lot. And then students are very upset when they realize that they were nowhere near the correct answer. But this is precise. There is precision here, but not accuracy. And I forgot to number these bottom ones. So let's say this is 3. This is accurate, but not precise. Why is it accurate? Because you do have a value that is in the bullseye, and they are all surrounding the bullseye. So they are accurate in that they are close to the true value, but they are not precise because they're completely spread out. And then you have one that is completely off. It's not even on the board at times. It's not near the true value. Yes, there's one, but unlike this one that is surrounded around the true value, this one is not. It's completely just off to the side. So this is neither precise nor accurate. So now we're going to actually start getting into the real chemistry, and this is a section that students have problems with. And it's something that you have to work at. I can teach you how to do this, but if you don't take it serious and you don't work on it, it's not something that you will learn. Very few people pick up science very, very easily. And this is something then that becomes a problem and an issue because you think you got the answer right and you email me and I tell you don't, because if you don't follow the rules, it doesn't matter if you have the value right. You have to have the same number of digits in order for it to be right. So say that the answer calls for 3 digits and you give 4, your answer's wrong because you didn't follow the rules. And this is a part that students have a big problem with. So I actually just put up on Chem 101 for one class, I will do it for the other, is practice problems involving sig figs and exact numbers and measure to help students understand what you need to do. This is not graded. It does not count at all. And it's on the system that we'll be doing quizzes and exams on. So I definitely suggest that you take advantage of the practice problems. It shows you if the answer is right or wrong, and it shows you how they came up to the answer. And that's what a lot of students need, is to see the breakdown. Okay, so a set of rules we follow when dealing with measurements and calculations. When rounding calculated numbers, we pay attention to sig figs. So you might see me put SF, which is abbreviation. So you do not overstate the precision of our answers. So we are going to be dealing with a set of rules that we follow when dealing with measurements and calculations. When rounding calculated numbers, we pay attention to significant figures. We never overstate the precision of our answers. The last digit in our answer is the estimated digit, the digit of uncertainty, and I'll give you examples. Some of the things that are involved in this are understanding measured numbers. Measured numbers are anything that we measure. That's it. It's that simple. Is it measured? Then it is a measured number. We deal with exact numbers. Exact numbers are not measured numbers. They are counting numbers, meaning 12 eggs, something you can count. 4 chairs, something that you cannot say a chair is 1.75 of a chair. It's a chair, 1 chair. You can't take away from that. You see a chair. 1 person, something that can be counted. 4 apples, 16 apples, 3 peaches, so forth. So there's a difference between measured numbers and exact numbers because there's different rules for these. Significant figures refers to the digits that were measured. So we're looking at measured numbers. So what are measured numbers? Measured numbers are numbers that when you measure something, height, weight, temperature, we're gonna measure things, and if it's measured, it is a measured number. So to write a measured number, we have numerical values. So let's take a look at this metric ruler that's in centimeters. So if you have a ruler that's in inches, if you flip it, the other side is usually centimeters. So we're going to measure this screw, but not the head of the screw, just the everything but the head. So we observe that there are numerical values of the marked lines. We estimate the value of the number between the marks. The estimated number is the final number in your measured number. This is the digit of uncertainty. So let me show you how to read, because you will be tested on this. It will show up in your experiment. You will be expected to know how to read things that have increments like this and read it correctly, and you'll be marked wrong if you're not. And the same goes for barrettes and graduated cylinders and things that you probably haven't encountered in lab yet. So let me show you how to do that with this. This is centimeters. This is 1 centimeter, 2 centimeter, 3 centimeter, 4. That's what this picture is showing. Look in between so we can take 2 and 3 and count how many lines there are between 2 and 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 lines in between 2 and 3. So this is, the main numbers are 2 and 3, and there are 10 lines, or 10, it's divided into 10 lines in between. That means that this is an increment of 0.1. So it's in the 10th place. Why? Because this would be 2.1, 2.2, 2.3, 2.4, 2.5, 2.6, 2.7, 2.8, 2.9. These are numbers that you can absolutely measure. You know that it is correct, that you are certain of, but anything that falls in between, you don't. And that's where the problems are. So if we look at this screw here, we can see that it passes 1. So we're definitely certain that this is past 1. We count the increments, so we know that this, if there's 10 lines in between, it is in increments of a tenth. So 0.1, 0.2, 0.3, etc. So We are certain that this passes 1. We are certain it passes 1.5. We are certain it passes 1.6, and we're certain it passes 1.7. However, if you look at the screw, it's in between 1.7 and 1.8. This is where the estimated digit comes in. You might see it as something, somebody else might see it as something else. That is the digit of uncertainty. So in this case, if you look here, we know the 1 and the 7 are certain. So if you look in between these two lines, I'm going to say that this is the middle of both of these. So that means a 5. So my answer here is 1.75. I underlined 5 to show you that's the digit of uncertainty, because somebody else might say it's 1.76. Somebody else might say it's 1.74. 1.75 centimeters. This is not an easy thing for students to comprehend. This is something you need to work on. A lot of what's in chemistry will not come easy unless you are science oriented. And a lot of students get upset because they don't feel that the course is giving them what they need to learn. And I will tell you right now, you may not agree, it does. It gives you a lot to learn, but the problem is it's like calculus. You have to keep with it or it doesn't make sense. You can't wing it. You can't just use, honestly, you should be reading between an hour and 2 hours every night during the week to make sure that you comprehend this. If you do that, you will never have to study when a quiz and exam comes up. But you definitely should be putting just on the lecture side. This doesn't even involve the lab side. This is the foundation. If you don't have a strong foundation, you will struggle through this whole thing. I can give you every answer and you will still fail, because chemistry is not about memorizing. It is about actually learning. And if I change one thing, you fail it. And that is where students have a hard time understanding that. Why can't I help more? I'm giving you everything I can. I do help, but the effort has to be on your side. And introductory chemistry is sometimes really hard for students to understand that they have an idea, an estimate of how much time they are going to spend on a course. And it's never that. It's always double. And that's where the problem is. Okay, so certain digits and estimated digit. Remember, the last digit is always the digit of uncertainty. So if we look at this number here, the first 4 digits are certain. We know that. Let's say we measured this. We know that those are certain. The last digit is estimated. The greater the precision of the measurement, the greater the number of significant figures. Remember when I told you the more numbers a value has that's measured, that's the greater precision. But there's rules for that. We have to make sure we follow rules to show that if we give a number that has a lot of numbers in our answer, and that means greater precision, we have to have things to back that up. We can't just throw that out there randomly. So chemistry, that's why we have all these rules to make sure that when somebody publishes a peer-reviewed paper, that their experiments can be, done again over and over, and we can come up with the same information. Okay, so significant figures shows how precisely the data has been measured. Greater number of significant figures means the measuring tool is more precise. Remember the animal on the animal scale and the analytical balance? Perfect example. Incorrectly adding more significant figures makes it seem that you have more precision than you really do, and that is inaccurate information, false information, and that could get you in a lot of trouble. And just like in most fields, your reputation, if you're putting out this stuff, it means everything. Not having enough sig figs makes it seem that you have more precision than truly exists. Not having enough. That does not sound right. Not having enough sig figs makes it seem that you have less precision than truly exists. I apologize for that. Not having enough sig figs. There. Disregard this sentence. I did not catch this because this is a repeat. This is the one. Not having enough significant figures makes it seem like you have less precision than the measuring tools provided. So it's worse on one way and it's worse on the other. You have to follow the rules. So what does sig figs not tell you? If the measurement is truly accurate. All it's doing is giving you a value. It's not telling you if it's close to the correct value. It's just giving you a value. So again, precision is a measure of how close a series of measurements are to one another, but not necessarily, it has nothing to do with the true value and how close it is to that. Let's take a look at these two instruments that you would use in the lab. I should have wrote the names of these so you would understand. This is a beaker and this is a graduated cylinder. And what you do is, one, you never, ever, ever use a beaker to measure volumes that need to be accurate. This is approximate, And if you were in lab with another person, you guys could compare beakers and you would notice that these numbers would be slightly off from each other. So it's approximate. So if you need approximately 80 mils, you could use this. But if you needed 66.3, don't use this. This would be off. So when we look at significant figures, you can tell that 2 digits, this is not very precise. It is less precise than something that has more significant figures. How do you know that? By just looking at it? Though there's less increments here too. So that means that this is not going to, you're going to estimate on this last digit. You're not going to estimate in the ones place on this one, because there's the 1. You're going to estimate on the tens place. And that's going to tell you that this is going to be more precise. So you always have to figure out how, when you're looking at any of these numbers on a ruler, on graduated cylinders, you have to determine the divisions. What is it broken up between the 2 numbers? That's going to tell you the division. You always go one past what you know. So in this case, let's see, this is 20, 30, 40. So this volume, and one, you always look at eye level, and you look at if it always goes like this. And you take the bottom part of it, and there should be more examples in here. If it's not, it'll be in lab. So here we know for certain that 40, the water is past 40. It is not, however, to 50. So my digit of uncertainty is going to be this 8. So this is going to be 48. Some might say 49. Some might say 47. This is only 2 digits. Look at the divisions, count them, and then look at what you know for sure, and that will help you understand how to read this. So let's read this one. This is increments. Look at 10 to 20. So this is 10, 11, 12. This is not 0.1. This is not tenths. The other one was tenths, but this is 10. So if we go back, this is 1. This is not 2 because 2's here. So this is 1, 1.1, 1.2. So that's how you should be able to tell that. Can you go from 1 to 2, the next number? If you can't, then that means that you're dealing with tenths place. On this one, you go from 10 to 11. You can't go 10.1 because this would get you to 11. This should be 11, and it's not 11, it's 20. So this is in ones. So this is 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. So let's go up here. So if I know that this is in ones, then my estimated digit has to be the tenths place. So it's always 1 less than what you can determine. If you get confused, write down what you can understand. So you can write down here like 10, 11. Then that means that your next digit is going to be I told you to add another digit. That's your digit of uncertainty. So here we know that we passed 40. We passed 45. We passed 46. And remember I told you this concaves down. We don't read here. We don't read here. We read at the lowest point in the middle. This is, I'm going to say 47, and I'm actually going to disagree with this, and I'm going to say that this is 47.0, not 47.1. But this is why it's a digit of uncertainty, because somebody else might say, no, I'm wrong and blind. It's 47.1. That's the 0.1 is the digit of uncertainty, but this gives more precision. This gives less precision, less digits. Okay, so now let's go over the rules. And these rules are things that you definitely should learn, memorize. I know you're at home, but this is something, if you memorize these, it will absolutely become very easy to understand. Answers will follow you all through chemistry. And from this point on, once you learn chapter 2, you are expected to follow the significant rules on every assignment. And this is where people will have a hard time. They're like, well, I didn't know that. Well, this is why you learned it. Chemistry's implied. Once they give it to you, they expect you to keep it and retain it till your dying days of chemistry. When you're done, you will follow these rules. So this is certainly a foundational information section. Definitely you need to work on this and understand it. And memorizing it, learning the rules will make your life so much easier. Okay, so all non-zero digits are significant. All between non-zero digits are significant. What does that mean? Okay, well, if we look here, if you have no zeros in your value, they're all significant. This is a measured value. We're going to say all of these are significant. Excuse me. If you have a zero sandwiched between numbers that are not zero, that is also significant. If a decimal point is present, zeros to the right of the last non-zero digit are significant. So what does that mean? That means that this is sandwiched, so that one applies to this one. This one is this rule. But we have 2 zeros here. They are after, key being after the decimal point. All these numbers here are significant. Any zeros that show up after the decimal point are significant. So this is 3 significant figures. Okay, zeros to the left of the non-zero numbers are never significant. So we have zeros in front of this. We have zeros in front of this. And even though there's a decimal, I just said after the decimal, they're important. But the difference is there's a number here. Then there's zeros. Here, the numbers come after the zero. None of these are significant. Why are they not significant? Because we could change these values into scientific notation. And once we put these in scientific notation, we can kick these zeros out and they don't exist. Because we would use a 4.5 times 10 to the something, 1.2 times 10 to something, and they're gone. So we can get rid of them. So they are not important. They are not significant. So this is 2 sig figs. This is 2 sig figs. So how many significant digits are in 4.5 millimeters? 2, 2, and 2. So this just shows you these zeros, they're just placeholders. Remember, tenths, hundreds, thousands, 10,000s. Remember I told you definitely need to learn your placeholders. That will help you. This is where it's going to come in. Because as you start doing math, and what messes up people in chemistry, here's something that people don't like to hear. What messes you up in chemistry is not the chemistry, it's the algebra. Because very few people retain the algebra and they get stuck that it's chemistry. It absolutely is not. It is algebra that's going to get you, not the chemistry. So the sooner you understand the places of these digits, that will save you some. Okay, so identifying significant digits. If there is no decimal point present, zeros to the right of the last zero may or may not be significant. You need more information. If you didn't have enough information, then you would have to make a determination. So for instance, there's no decimal point here. So I'm going to tell you this here is 2 sig figs because we don't know whether these are significant or not. And because I need to give an answer, I'm going to say 2. Here, I'm going to say this is 1 significant figure. I don't have enough information. This has to have a decimal point here. Then all of these would be significant. This would have to have a decimal point here for all of these to be significant. So this is a 1. This is 1, 2, 3, 4, 5. 5 significant figures because these zeros are sandwiched in between 2 digits that are not 0. And these are 4. So they may or may not be significant. You would need more information. But if you were given these values on a test, I would tell you this is 2, this is 1, this is 1, these are 5, and this is 4. Okay, so defining significant digits for large numbers. So if we look at this number, this is 10,000 kilograms. We measured it within 100 kilograms, plus or minus. So that means that for here, this value is can be between plus or minus 100 and still be in the range of our value that we are interested in. I don't tend to use this plus or minus. They do in the lab more. When you're actually doing lecture portions and given numbers, you're expected to give an actual value. But you should understand what this means. That this means that this value, there's a value that it's like the estimated digit. This could be 100 up to 100 more and up to 100 less. That's what this means, of plus or minus. So if you're given something like this, then it means that these first 3 sig figs are, these are the 3 digits are considered sig figs. Anything after that, notice these are 3 digits here. So 1, 2, 3. So after that, these last 2 are not. That's where that's the estimated where it could go up and it could go down. But we definitely can say that these here are significant. This is why I'll be honest, I don't really care for doing this because it's a little confusing. So I tend to stay away from this. I didn't get to pick your assignments on homework. But for quizzes and exams, I tend to stay away from stuff like this. So that's a good thing. So you can also write this in scientific notation, 1.00 meaning 3 sig figs. Anything that shows up in scientific notation that's written on this side of the multiplication, these are considered sig figs. And then 10 times to the 4th kilogram. Okay, so summary of significant digits. We show significant digits show precision of a measured quantity. That means the more numbers you have, the more precise it is. Significant, non-zeros. Anything that's a non-zero in a value, they consider significant. Zeros between non-zeros, sandwiched in, they are significant. Zeros after a decimal point when you have non-zero numbers in front, those are significant. Zeros to the left, before you have actual numbers that are not zero, we can kick them out because we can write these numbers in scientific notation. We don't have enough information on this last one, so we would need more information, or you would just take this as face value and they would say this is 2 sig figs. And but if there was a decimal here, all of this would be significant. This is a little fuzzy, but this is a chart I got from one of my other classes. It gives you an example, so if you get confused, you can refer back to this, and this would help you understand to an extent. It tells you the number of sig figs, and it gives you examples of measured numbers. So sometimes I'm a visual person. I need some examples to help me understand something. I just can't read it and accept it. So this is something I'm giving you guys. Okay, so again, this is from another course. I went over the slides that your book gave you. These are from another course. I break it down the same way, but with examples. I learn from examples. Here is a summary of significant figures. So again, all non-zeros, so you can see trap zeros and non-zero digits. These are all just examples to show you. Zeros at the end of numbers without decimals are not significant. So here is for me to show you 1 sig fig, 3 sig figs, 2 sig figs. Remember that you don't have enough information, but if you were given any of these, you couldn't say you don't have enough information. You would, so I kind of hate when they say that, because you're still expected to tell me how many sig figs you have if you have something like that. This doesn't have a decimal point. If it did, it would be 2. This doesn't have a decimal point. If it did, it would be 3. This doesn't have a decimal point. If it did, it would be 5. And the same goes for here, would be 4. So the decimal point and where it is makes a big difference. Now let's look at exact numbers. Exact numbers are some things you can't say it's a tenth, a hundredth, a thousandth. You count them and that is it. So 7 pennies, that's what you see. You don't have 7.25, 7.3, you have 7 pennies. That's exact. Defined values. Defined values are also exact. They mean conversions. Conversions between the same system. This is a metric system. So 1 gram is equivalent to 1,000 milligrams. This is exact. We say that these are exact. We would never count them in the significant figures rules. We would never count this in significant figure rules, and we would never count these conversions in significant figure rules. This is the same counting system. 3 feet equals 1 yard. Never would count these in our significant figure rules. And you will learn that as we go on. So exact numbers are not measured, and they do not have limited number of sig figs. So what this is really saying, they don't really state it, but what this is that this is 1.00000 to infinity. This is 1,000.000 to infinity. Same thing here. So you couldn't count the zeros because it's infinity. And exact, we don't mess with them. It's saying 7.000 because we just count it that way. That's what they mean by do not have a limited number of sig figs. Not used to find the number of sig figs in a calculated answer. This is where some students get confused. I will go over that. I put up a practice problem and I break down the problems in it, and I cover some of this in there. Numbers obtained by counting 8 cookies, 6 eggs, 10 chairs, they are exact, do not follow significant rules. Only measured numbers. Definitions that compare 2 units in the same measuring system, we do not count in sig fig rules. So when we start doing calculations, these are things that you need to remember because they will really make a difference on your answer. So we don't count this and we don't count this. So here are examples of exact numbers to help you understand. This is from another book I taught. So you can see the same system, same system, same system, same system, same system, same system. Exact means we don't count them. All right, so let's do some, again, when I put this together, I did not have access to the homework. So I took slides from my other classes. Identify the numbers below as measured or exact and give the number of significant figures. Okay, so I'm just going to jump in and we're just going to break this down. You have 3 coins. That is a counting number. If it's a counting number, it is an exact number. We do not count sig figs. They are infinite, is how they put that. Second one, the diameter of a circle is 7.902. That's measured. Because it's measured, it is, we have to follow the significant figure rules. We have a 0 in between, that is sandwich, so it counts. So this value has 4 significant figures. And 60 minutes equals 1 hour, and 1 hour, that is a same system. So we would not use that for significant figures. It's exact by we call definition. And in chemistry, we use H, not HR. I put up a practice problem where I used HR because at that point we hadn't covered chapter 2 yet. So I didn't want to confuse people, but once after we're done with